JavaScript has a reputation for being single-threaded. This means it can only do one thing at a single moment in time. Imagine a single lane of traffic. Only one car can pass through at any given point. If one car stops, the entire line of traffic behind it comes to a halt. This is what we call blocking. JavaScript, by its fundamental nature, works in this exact way. It processes one command, then the next, and so on in a strict sequence. This single-threaded model is simple and predictable, which makes writing code easier to reason about in many scenarios. However, the modern web is complex and interactive. Users expect to click buttons, scroll pages, and fetch data from servers without the entire application freezing. If JavaScript could only do one thing at a time, any long-running task like a network request would freeze the user interface completely. This would create a terrible user experience. The browser would become unresponsive until that single task was finished. To solve this problem, JavaScript environments like browsers or Node.js, provide us with tools to handle these long-running operations without stopping everything else. These tools are the web APIs. This is where the magic of the event loop comes into play. It is the core mechanism that allows JavaScript to feel like it's doing multiple things at once, even with its single-threaded constraint. The event loop is a constantly running process that manages and coordinates the execution of code. It's what lets us write asynchronous code that can start a task now and finish it later, without blocking the main thread. It works behind the scenes, orchestrating the flow of operations between the JavaScript engine, the web APIs, and the various task queues. So, the event loop is not part of the JavaScript engine itself, but rather a feature of the hosting environment. It is the unsung hero that enables a responsive and dynamic user experience. It creates the illusion of concurrency, making JavaScript powerful enough for today's demanding applications. Think of it as a traffic controller for JavaScript's single lane of code. It ensures that traffic keeps moving smoothly, even when some cars need to take a detour for a longer task. Understanding this controller is the key to mastering asynchronous JavaScript and building non-blocking applications. To understand the event loop, we must first look at its two most important companions, the call stack and the task queue. The call stack is a data structure that keeps track of where we are in the program. When a function is called, it is pushed onto the top of the stack. When that function finishes and returns, it is popped off the stack. This happens for every function call in your synchronous code. It's a last-in, first-out system. If you call function A, which then calls function B will be on top of the stack, followed by function A below it. Now let's consider asynchronous operations like setTimeout. When the JavaScript engine encounters a call to setTimeout, it doesn't handle the timer itself. Instead, it hands this task over to a web API provided by the browser. The web API starts the timer in the background. Meanwhile, the JavaScript engine doesn't wait. It continues executing the next lines of code, keeping the call stack clear for other synchronous tasks. This is how JavaScript avoids getting blocked. It delegates the waiting to another part of the environment, freeing itself up to handle other business. Once the timer from setTimeout completes, the web API doesn't just interrupt the JavaScript engine. That would cause chaos. Instead, the callback function associated with the timer is placed into a waiting area called the task queue, or callback queue. This queue is a first-in, first-out line. Functions wait here patiently for their turn to be executed. They are not yet on the call stack. They are simply queued up and ready to go. The task queue holds all the callback functions that are ready to run after their corresponding asynchronous operations have finished. The event loop has one simple yet critical job: to constantly monitor the call stack and the task queue. Its rule is straightforward. Is the call stack empty? If the answer is yes, it checks the task queue. If there's a task waiting in the queue, the event loop takes the first one and pushes it onto the now empty call stack for execution. This cycle repeats endlessly, checking the stack, moving tasks from the queue, and ensuring that asynchronous callbacks are executed only when the main thread is free. This continuous process is what gives the event loop its name. The story gets a little more detailed when we learn that there isn't just one queue. There are actually two main types of queues that the event loop manages: the macrotask queue and the microtask queue. Understanding the difference between them is crucial for predicting the exact order of execution in complex asynchronous code. The task queue we discussed with setTimeout is more accurately called the macrotask queue. Tasks like setTimeout callbacks, setInterval callbacks, and I/O operations are placed here. They are considered larger, separate units of work. Microtasks, on the other hand, represent smaller tasks that need to be executed very soon after the current task completes. The most common source of microtasks is a promises then, catch, or finally callback. When a promise resolves or rejects, its associated callback function is not placed in the macrotask queue. Instead, it is added to the microtask queue. This queue has a higher priority than the macrotask queue. Other sources of microtasks include queue microtask and mutation observer callbacks, which are often used for fine-grained DOM updates. The event loops rule needs a slight update. After a task from the call stack finishes, the event loop does not immediately check the macrotask queue. First it asks, are there any tasks in the microtask queue? If there are, it will execute all of the microtasks in the queue, one by one, until the microtask queue is completely empty. Only after the microtask queue is empty, will the event loop proceed to take just one single task from the macrotask queue to execute. This process then repeats. Let's see this in action with a code example. Consider this code console log start. setTimeout, =console log timeout, 0, promise resolved. Then, =console log promise, console log end. The output will be start, end, promise, timeout. Here's why. Start and end are logged synchronously. The setTimeout callback is placed in the macrotask queue. The promises then callback is placed in the microtask queue. After the main script finishes, the event loop empties the microtask queue first, logging promise. Then it processes the macrotask queue, logging timeout. Grasping the mechanics of the event loop, including the call stack, macrotask queue, and microtask queue, is not just an academic exercise. It is fundamental to writing effective, predictable, and performant JavaScript. Without this understanding, you are essentially flying blind when dealing with anything asynchronous. You might see unexpected behavior in your application, where code runs in an order you didn't anticipate. This can lead to subtle bugs that are incredibly difficult to track down and fix, especially as applications grow in complexity and rely more on asynchronous operations. Knowing how the event loop prioritizes tasks allows you to structure your code with intent. For example, if you need an action to occur immediately after the current script has finished executing, but before the browser has a chance to do anything else like rendering or running a timer callback, you would use a microtask like a promise. This gives you fine-grained control over the timing of operations. This level of control is essential for building sophisticated frameworks and libraries that need to manage state updates and UI rendering in a highly efficient and predictable manner. Furthermore, a solid mental model of the event loop helps you write code that is non-blocking and responsive. You can confidently use asynchronous patterns to handle long-running tasks like fetching data, processing large files, or responding to user input without freezing the main thread. This directly translates to a better user experience. A user will never have to see a frozen screen while waiting for data to load. Instead, they can continue to interact with your application because you have properly delegated the waiting to the browser's APIs and the event loop's queuing system. In conclusion, the event loop is the silent engine that powers modern JavaScript. It transforms a simple, single-threaded language into a powerhouse capable of building the rich, interactive experiences we expect on the web today. It is the bridge between synchronous execution and the asynchronous world of events, timers, and network requests. By taking the time to truly understand its cycle, the interplay of the call stack and the different task queues, you move from being a developer who simply uses JavaScript to one who truly understands how it works. This knowledge empowers you to write better, faster, and more reliable code.